So come back to this diagram. What is the pressure on the left-hand side? In what direction and in what orientation? Pressure here. Direction. Direction.
Inward and normal.
Inward and normal, yeah, please don't surprise me. Inward and normal, right? I don't care which direction the flow is. Inward and normal. So now that's my theta, P. What about the pressure on the right-hand side? After I move a distance of ds. Which direction? Again, just tell me the direction. Inward and normal, which is pointing to the left or to the right? To the left or to the right? Which is left, which is right, right? This side. Do I need to tell you which way the flow is going? No, we don't care. Inward and normal. So which side? Which way? To the left. And this is my theta, so I have P plus now dP. Okay? And using this differential analysis, the dP, this term is equivalent to d theta dx, which is now replaced by d pressure versus ds in the s direction. Do you see that? As such, the difference between these two forces, which have to multiply by the area, is the net, the d theta term here, where the pressure cancel. So I have partial of P with respect to S, times the distance I move ds, times an area. What's that area? Because pressure times an area give me a force. What's the area? Over that pressure acting on? dN. I need one more dimension. dN times pressure.
Yeah, why would it not be in the negative direction?
I haven't finished.
Okay.
Right. So, yes, it should be negative. So it's dN times 1. Do you see that? So I'm putting all this together then. Where my F equal to MA is now equal to everything put together. That's my force, simply due to differential pressure. This is my differential mass. The last term is my acceleration in space. And if you remember your calculus, when you do this type of formulation, the characteristic is a lot of the independent variables. What do I mean by that? All the dN, ds, that's the coordinates, will cancel out. Will drop out in the final form. And what we've shown then, with a lot of somewhat strong and dense, is this equation now describes how my acceleration in space will occur as a function of the pressure gradient, and it's negative. Meaning as the pressure drop, my flow accelerate, and vice versa. So later on, we're going to take this equation and show you how the Bernoulli equation comes about. But let me stop here and give you a chance to ask questions on all the intricate new concept, acceleration still occur when it's a steady problem, differential formulation, etc., etc. Does that make sense to you, what we have done? Are you comfortable with doing a homework similar to this? Are you ready? Questions? So your homework is very similar to what we have done. In the normal direction, prove to me that the equation of motion for inviscid fluid under the same assumption will be shown to be like this, where in a streamline, where it has some curvature, meaning the flow is not going straight and parallel. The radius of curvature R is defined from the point of interest to the center. And it appears here on the right-hand side. Do you see your homework as to what needs to be done? No? You're going to follow the same approach on the differential analysis. Find out the force due to pressure in the normal direction. Find out the differential mass, which you should know. And find out the acceleration in the normal direction. So I'll give you some hints. What is the acceleration of this particle when I'm spinning it like this? Where the radius of curvature is my arm. Is there any acceleration? Just v squared over r. You have to decide in what direction. Okay? So that's a relatively simple exercise that I hope to reinforce what we have done in terms of the first time that you're dealing with a differential equation formulation. So that's a baby step. At least you get a hang of it, then a month from now when I look at a three-dimensional problem, you can recall all this fine detail. All right? Okay? Very good. So now I'm ready to show you how this Bernoulli equation comes about. So we're going to start with the equation that I just proved to you. I'm a little sloppy in my differential operator in that the partial derivative and the exact derivative, I kind of use them interchangeably. It's all correct within the context of what we are doing. So this is what we have shown you just momentarily, and it requires a streamline in the flow field, and the direction of this equation applied to that direction along the streamline. So I'm going to rearrange this algebraically. Just to simplify that. And I'm not going to do that in the class, in the lecture, because it would take more time and it's nothing but algebra. I'm asking you to read that yourself in the text. If I add gravity in this column, there will be additional force term. on the left-hand side. And if you go through that, the equation then will be adding the body force. So this term, I'm not going to deal with. It's just algebra, same physics. So the force term on the left, F, has to be added, a gravitational term, which can be shown in the text, and in your reading you'll find it out, how to account for that. So now I have this differential equation for Euler in the S direction. What do you think I will do next to get Bernoulli? Any guess? You integrate. You integrate. So I'm going to list out the assumption up to this point before I integrate, which are frictionless and steady. I didn't neglect gravity, so I shouldn't say that anymore. Inviscid steady. So notice I'm missing two of the other assumptions. And they will be added as we progress gradually to the final Bernoulli equation. So why do I have an assumption that Bernoulli can only apply when I can identify a streamline? This is right here now. Because in order to integrate, I have to integrate along my streamline from point 1 to point 2. If I don't have a streamline, I cannot integrate. Flow that is turbulent, flow that is chaotic, I can't use Bernoulli. So the next step of the integration looks similar, very similar to what I have in the final form of the Bernoulli equation. So right at this step, I'm adding along a streamline. So when you do your derivation as a homework, I want you to think, and this is a very difficult concept to convey. Up to this point, I make no assumption about the fluid density being constant. And I want you to think about why. Okay? And what? Up to now, I'm trying to show you sequentially all the four conditions. I have three now, I have the fourth one. So the derivation as shown up to now, make no assumption about the density in my differential element being constant. It's not easy to answer, but I will go on to that until next time. But the last step where the incompressible assumption comes in is in this last step. In order to integrate this mass differential, my density must be constant. Do you see that? And that is now my Bernoulli equation. From first principle of particular MA. The more conventional form that we have used for many problem solving is P plus half rho V squared plus rho GC equal to a constant. And that's how it comes about. So I spent a good part of a half hour on this, and there's very important implication of it. And I will go through that next, but do you understand why all these four assumptions are needed? No more, no less. Yes,
If you were to find some function of density based on pressure, could you then apply Bernoulli's to, like any fluid?
the answer is yes. You would use Bernoulli, not at this final stage. And for that reason, I can argue that it's no longer Bernoulli. You can start from here. Okay, the answer is correct. If I give you some problem where I give you the relationship of how the density change with pressure, yes, you can still use this equation. But it's very unconventional because the only reason we use Bernoulli is it's a closed form, very easy to use equation. And we have taken advantage of it in many problems. Give us some ballpark number that for many engine applications will be sufficient. Like trying to find the anchoring force on the nozzle. You don't have to be 1% accurate. You could be off by 10%. Just use a bigger boat, right? Can't do that for aircraft engine in the hallway. You're not going to carry that weight. You need to be 1% accurate, or else. So this is all good for elementary fluid mechanics. And when you go work for a company like General Electric designing either gas turbine or steam turbine, you're not going to get a salary of $70,000 a year doing Bernoulli and control arm, because they won't cut it. You're going to do a three-dimensional equation of motion of Navier-Stokes that include also the viscous effect. You put on a computer, you try to simulate a flow. That's what your job is. Right. So this is all basic and fundamental to kind of get you to think about all the physics and the logic. Okay? Questions on how the Bernoulli comes about and why these four assumptions are so critical? Okay, I'll take a 2 minutes break and then we come back look at some of the problems of your homework.